My name is Olivia Nitko, and I am the developer of Ecospat, a Python package and web application designed to categorize the range and population dynamics of species through time using existing GBIF data in order to predict the persistence of individuals and populations under climate change. Ecospat has significant biological relevance, especially under climate change. By breaking a species' non-contiguous range into edge categories of leading, core, trailing, and relic zones, we can identify the genetic and functional attributes of these different populations. However, species ranges are also moving in response to climate change, with large effects on persistence. Species are expected to move poleward to track their climate envelopes, but not all ranges are moving as expected. For example, ranges can also remain stable, pull apart, or even reabsorb back into the core zone of admixture under climate change. Ecospat provides these insights and more to construct species ranges, classify them into one of the four movement patterns, and calculate the relative density of occurrences within range edges through time. This information is important to understanding species' response to climate over decades, and range movement type can readily be integrated into GBIF as a new categorical tool. Using this information, Ecospat also generates the propagule pressure, or the likelihood of individuals arriving in an area from nearby sources. Ecospat also predicts the persistence of individuals at 1 and 5 year intervals to assign a risk decile based on divergence from baseline mortality. Every search begins with a species' scientific name. This can be any species of your choosing. However, if a species does not have adequate occurrence data, it will return the start window. Ecospat also provides both simple and advanced filters that are important for basic functionality and user specification. These values can have a large impact on the inferred range dynamics of species and individual persistence, which is why we provide some recommendations. For example, the GBIF limit represents the maximum number of GBIF records to use. Based on a preliminary power analysis, we recommend using 2 to 4,000 occurrences. The bounding box, or the extent of occurrence, is another important parameter given that species can have variable range dynamics across regions. We recommend searching each region separately for globally distributed species. Start year is also required for species not included in Little's historic range maps of North American tree species. We recommend choosing something that is in the 1970s or 1980s, as many species do not have adequate occurrence data before this time. The end date represents the end of the modern distribution. It is also auto-updated to reflect the current date. This will not often be changed unless a user only wants to calculate range dynamics up until a certain year or date, for example 2020. Users can also choose to use occurrences of a specific nature, for example, human observations or living specimens. If the user does not specify, all geographically valid occurrences are used. As for the biology, the baseline mortality represents the annual mortality of the species. This can vary widely by species, and we recommend consulting the literature for more information. However, the default is set to a 10% annual mortality rate. Distance decay and directional modifiers are more advanced filters and are used in the generation of the propagule pressure raster. These default values work well as constants and should only be changed if you have information regarding the dispersal ability of a species. Finally, users can also specify propagule pressure raster resolution. Currently, the default is set at 0.167 degrees or 400 kilometers squared. This resolution can be made finer, but will increase computational time. We will analyze the range dynamics and persistence of narrowleaf cottonwood or Populus angustifolia using 2,000 occurrences in North America. Because this species is included in Little's range maps of North American tree species, we do not have to specify a start year as this will be assigned internally. So this is the output of Ecospat. As we can see here, the different elements of the historical range, including these large core zones of admixture, followed by these trailing edges, and north here are the leading edges. We can see something similar here with the elements of the modern range distribution, where we have these large core zones, followed by these trailing populations and the leading populations in the north. Now, these historical and modern distributions can be compared in order to determine that Populus angustifolia has a stable range dynamic. And these summary statistics can also be downloaded and will reflect what we're seeing here in the web application. Additionally, we can also download the historical range CSV or the modern range CSV, which provides information about the different populations, their range edge categories, their area, and then the number of occurrence points found in each population. Additionally, if we look down here, we can also see the propagule pressure raster, which can be downloaded at both the range extent as well as a global extent. Here, if we download it to the range extent, it will be downloaded as a .tif file and looks something similar to this. Finally, moving on to the individual persistence map, we can see that individuals within the same population can have a different predicted persistence. So for example, here in this core population, an individual in the north has a relatively high predicted persistence at 5 years, yet an individual in the south of the same population can have a very low predicted persistence, this specific individual having the highest risk decile. This information can also be downloaded, and this CSV provides information about the predicted persistence at 1 year, predicted persistence at 5 years, where these different individuals are located, as well as more information about their deviation away from baseline mortality. So what could this mean for you? Sarah, Amy, Michael, and John are neighbors, avid naturalists, and citizen scientists that live in Halifax, Nova Scotia, Canada. Recently, they've noticed a worrying decline in the conifers surrounding their communities, cities, and wilderness areas. They decide to use GBIF to see which conifers are common across Nova Scotia. They find that balsam fir, red spruce, and white pine are widely distributed across their local community and provide valuable services and functions. They've been using tools to record occurrences for these species for years, but do not have information on the relative location or predicted persistence of individuals. With limited resources, they need this information to focus their efforts. And so they search Ecospat for information on these species to find that both balsam fir and red spruce are in their core zones in Halifax, and their individuals are doing quite well in the surrounding areas. In contrast, Ecospat suggests that Halifax is a leading edge for white pine and that these individuals are likely imperiled in the near future. Based on these factors and the locational distribution of predicted persistence near them, they decide to focus on monitoring individuals of white pine in the nearby wilderness area for mortality, insect, and disease. Through this manageable and biologically informed conservation plan, this group works to promote the spread and persistence of white pine in their natural areas and local community, transforming community science into community action. Ecospat is a fully open source Python package and web application that has been transparently developed on GitHub. The package uses an MIT license, and I welcome collaborative development and reuse. The most up-to-date version of the package is version 1.1, which is available for download on PyPI. The web application component of Ecospat is also publicly available on a Hugging Face space here.